Bismillahirrahmanirrahim. On this very short video on linear DC machine, we'll solve end chapter problem 1.21. Now, if you have not seen my previous video, you must see that so you understand the basics. Okay, so just to give you an idea about the linear DC motor, we have these two rails and on which there is a bar and there is magnetic field from north to south, and when this is connected to a battery through resistance, this bar will move, and this is the concept of railgun actually. So this diagram represents something like this. Now let's go and solve the problem, question number 1.21, and we have couple of questions here. We'll take one question at a time. Now let's see the circuit. Voltage is given, this resistance is given, this length is important because the current flows from here to here or from here to here. So this length is 1 meter, and the flux density or the magnetic flux, magnetic field actually is 0.5 Tesla. So that is the flux density. The first question is, what is the initial force on the bar at the starting, and what is the initial current flow? So we have learned in the previous video or also in the book that the induced force is given by ILB, and at the starting condition the velocity of the bar is 0 because this bar is not moving at the start, and therefore from the formula E induced is equal to V velocity, B L, B is the flux density and L is the length. So E induced is 0 because there is no velocity, and if you plug in this into the formula for current in this circuit, if you see this circuit by KVL, you can write minus VB plus I into R and plus I induced is equal to 0, and from there we get this relation I is VB minus E induced over R, and plugging in the values 100 volt, induced 0, resistance 0.25, so the starting current is 400 amperes. Now what is the direction of this current? Obviously from the circuit we can see that the current is flowing from top to bottom. So this is the direction of the current. And now we can find the induced force, which is ILB. I we have calculated, L is 1 meter, B is 0.5. So the induced force is 200 Newton. Now what is the direction of the force? Is it going forcing right or it is moving left? For that we have to take into consideration the left hand rule. Left hand rule, Fleming's left hand rule is for motor. So this left hand rule, if we look, the flux is going inside the page, our flux is going inside our magnetic field is going inside the page. So this is the magnetic field, and the current is going down. So current is going down. That means our force is towards right. So this is how you determine the direction of the force. So F induced is towards. Now we come on to the B part of the question. What is the no load steady state speed of the bar? And we have learned earlier from equation 1.50 that the steady state speed at no load or just after the starting is given by VB over BL, and where SS is for steady state and V is for velocity. So plugging in the value 100 was the battery voltage and minus 0.5 B and 1 meter is the length. So the steady state speed at no load is 200 meters per second. Now we come on to the third part. If the bar is loaded with a force of 25 Newton opposite to the direction of motion, what is the new steady state speed? Okay, so this is the bar. It was moving right, so we are loading it with a force of 25 Newton, or let's say we are attaching a load of 25 Newton for forcing it to the left. So this is called applied force. So, and in case of a generator, the VSS speed will now change to E induced over VL instead of VB over BL. We have to keep this in mind. And for steady state, the applied force and there will be an opposite and equal induced force. They have to balance, only then this will be in steady state. And for that, F applied, we know is 25 Newton, is equal to F induced and is equal to ILB. So from here, we can find the current. F induced is 25 divided by LB, putting the value. So we have 50 amperes of current flowing through this bar. Now, what is the direction of this current? For this, we have to go to Fleming's right-hand rule, because that right-hand rule is for the generators. So if you see this force is on the left, our thumb is pointing towards the left. The magnetic field direction is into the page, so the second finger is pointing into the page, and so the middle finger is pointing down. That means the current is flowing down. So this is direction of the current. So now that we know the direction of current, we can write the KVL equation. So this will become an equivalent circuit. This is E induced now. Current is now flowing in this direction. So the equation will be minus VB plus I into R and plus E induced. And from here, we can find E induced to be VB minus IR, and plugging in the value, we get E induced to be 87.5 volt induced voltage here, or induced voltage here, as shown it here. So we have found the E induced, and now we can find the steady state, new steady state speed, VSS, is E induced over BL, and plugging in the value of 87.5 and 1 and 5, the new speed comes to be 175 meters per second. And lastly, what is the efficiency of the machine under these circumstances, that is, when it is loaded? So we know the formula of efficiency is given by P out over P in multiplied by 100%. The input power at this inlet or under this specified force is VB into I. VB is the battery voltage is 100 volt, but the current is now new current under load is 50 amperes. So multiplying this is the input power. And the output power of the linear machine under this condition will be with the new voltage. The new voltage or the induced voltage is into current. So the induced voltage is 87.5 and the current is 50 amperes. So the output power now is 4375 watt. And so plugging in these two values into the formula, we can find an answer of 4375 watt divided by V input 500 watt, which comes to be 87.5%. So I hope and this gives you an idea how to solve this type of a problem. I recommend that if you could not follow this, you must see my previous video on the linear DC machine. Thank you.